So far we have discussed about, so we were talking about dielectric constant whose formula we found that it was sigma upon sigma minus sigma p, where there were two plates here and it was filled with a dielectric constant here completely, and there was sigma charge density here on this plate, and on this plate there was minus sigma charge density. So on this side of dielectric there was some minus sigma p surface charge density, and on this side there was sigma p surface charge density. And this was the formula of dielectric constant. This can be written as C upon C naught, which can be written as epsilon upon epsilon naught, where C is equal to the capacitance. C is capacitance when dielectric used. When this dielectric medium of K constant, K value dielectric K is used, then C is the capacitance, and C naught is capacitance when vacuum present between them. When vacuum present between plates. So when dielectric is used, we call the capacitance C, and when there is only vacuum between, then the capacitance we call it C naught. And when there is vacuum, the epsilon value is epsilon naught, and when there is medium used, then we call it epsilon. So K constant can be written in these type of ways. These three forms of this dielectric constant. Now moving ahead, we have next topic is charging of capacitor and energy in the capacitor. So when there is a capacitor, let's say sigma charge density here, sigma minus sigma here, there would be some sigma p minus sigma p like this in the dielectric medium. Overall, let's say this medium has electric field E. This medium has electric field E, and the electric field we know that would be equal to sigma. The electric field between is sigma upon epsilon K, where K is the dielectric constant of this medium. So this is the electric field between, and the energy density is equal to 1 by 2 E square epsilon. So it means that the value of energy density is sigma square upon epsilon K square divided by 2. Now the energy in this volume, since let's say this width is d and the area is a, then the total energy E total is equal to density of energy multiplied by the volume, which is sigma square by 2 epsilon K square times the volume, which is A d. Now, well, here what should we do is I should write this formula of density E square epsilon by 2. Now if I multiply by d and divide by d, then this electric field times this distance will become potential difference V square. E into d is V, so E square into d square is V square, and the left part, this epsilon A by d, this is capacitance divided by 2. So this formula is of the total energy stored inside this capacitor, and this energy is stored, this tells that energy in capacitor is stored in form of electric field. which is between the plates. The electric field between the plates is what stores the energy in the capacitor, and this can also be written as QV by 2. Now let's talk about charging of the capacitor. Let's say this, and there is some voltage source here, there is some battery here, and I am taking some dq charge from this side. This both sides are initially neutral. Now what I am doing is taking some dq charge from this side and putting it here. So there is some positive dq charge here, negative dq charge here, so that the total system is balanced. When I take a dq charge from this system, then I will denote it by minus dq charge, and when I add this dq charge here, I will denote it by plus dq. So with time, the charge on these plates is dq on this side and minus dq on this side. So when what so let's say the charge at any instant present on the plates is, let's say, q here and minus q here at any instant of time during the charging process. So I will say that the charge present here is q, and the electric field between them, or I can say the charge is q, so the voltage is, so the voltage between them is q by c, and to move there is potential difference v across them, and to move a dq charge from this point to this point across this v potential difference, the work done is equal to v times dq. Combination of capacitor, combination of capacitor, that is simply when there are parallel. What does parallel means? Parallel means there are capacitors which, there are capacitors C1, C2, dot dot dot. There is same potential difference across them. So this end of all this, one end of all this capacitor will be at V1 potential, and one end of this capacitor will be at V2 potential, and the potential difference across each capacitor, for each capacitor, V1 is equal to V, V2 is equal to V, V3 is equal to V. So parallel combination means for all of them the potential difference is same, and that simply looks like parallel addition of the capacitor. This was a capacitor, this is a capacitor, I added them parallelly, so this is a parallel combination. And in such parallel combination, either you see this or you see series. In such parallel combinations, the capacitance, equivalent capacitance, is simply the sum of all these capacitance C1, C2, C3 and Cn. And in case of series means there are capacitors here, let's say C1, C2, C3, like this. There are capacitors here, and the charge stored, the magnitude of charge stored on all the capacitors here, let's say it is q, it is minus q, it is q, it is minus q, then it is q, it is minus q, on this will be plus q, and then on this will be minus q. So the magnitude of charge stored on each of these plate will be q. So q1, the charge stored on this plate is q1, on this plate is q2. So we say that q1 is equal to q2 is equal to q3 dot dot dot, all these are equal to q. All of them are storing the same magnitude of charge. This is series combination, and you can also determine this series combination like addition in a series. And in such case, the C equivalent of all these capacitor from between A and B is equal to 1 upon C1 plus 1 upon C2 plus dot 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 plus 1 upon Cn. The capacitance is added like this. So there is one identification of parallel is like this. Another identification is that all the potential V1 is equal to V2 is equal to V3 dot dot dot, all are equal to V. All potential differences are same in this case, and in this case all the charges stored Q are same for all in series case. Now capacitor is over. The next topic is susceptibility, electric susceptibility and polarization. Polarization in case of electric field. Polarization P, polarization P of dielectric in a field. When there is a dielectric medium, we know that it has atoms which under the influence of an electric field, the electrons start shifting in one direction, which leads to the delta positive charge at one side, and the side on which the electron is forced to move due to the electric field force. Let's say this electron is shifted in this direction, this will produce delta negative charge in this side. So this polarization of atom all over the body creates some sigma p charge at one side and sigma p charge density at one side. These are due to the delta p charges here and delta negative charges here. Here there is delta positive charges, and summation of all these delta positive charges divided by the total area gives sigma p. The total sum of all these charges in this at this end divided by the area, it is the sigma p. Now the question is that all the pairs of the dielectric in this case, let's say if we zoom this, we will see that there are atoms, they are neutral, electron is revolving like this. Now what happens is that when I apply electric field in this direction, electrons are forced in this direction, so an electron will start to be revolving around the atom like this. So what happens is that if you see this atom, this part is partially positive, this part is partially negative, this is partially negative, this is partially positive, again negative, positive, again negative, and again this is positive until we reach the plate and until the end of the medium. Let's say this is the end of the medium. There is no atom of the insulator after this dielectric. There is no atom at the right side of this atom of this dielectric medium. Then it will end at this delta positive and this will end at delta negative. And the sum of all these delta negative charges divided by the sum of all these delta negative charges divided by the area, that is the sigma p minus here. Similarly we will get sigma p here. Now there are all these charge pairs. We can say that this is a dipole moment, 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 this is a dipole moment. We can add the dipole moments like this, or we can also do this, that this dipole moment points in this direction, this points in this direction, but these two are at almost zero distance from this each other. So since the formula of dipole moment dp is equal to delta charge into length between them, since the length between them is about 0, so we can say that almost all of these dipole moments are approximately all these are 0. All these dipole moments are 0, and there is one charge left at this end, and there is one charge left at this end, and I have paired all these charges in between. Now what happens is that this length is d from this to this length, and the charge is sigma p into the area. The total charge at this end is sigma p minus, and at this side is sigma p a, and the distance between them is d. So the dipole moment of this whole the dipole moment generated in this the dipole moment produced due to the electric field in this medium would be equal to the total charge. Since this is equal and opposite charges here, we can treat them like a dipole vector dipole, and all these dipole vectors, let's say a vector connecting this charge to this charge, and then this charge to this charge, and then this charge to this charge, the sum of all these vectors, the summation of all these dipole moment vector give the p net vector, which is equal to the charge sigma p a into the length between them, which is t. So this becomes the total dipole moment vector. And what is polarization? Polarization is equal to the total dipole moment net generated in this medium divided by the volume of this medium, which is equal to, this value is equal to sigma p, let's say this direction is n cap, sigma p ad n cap divided by the volume ad. So this will become sigma p n cap. So the dipole moment, so the polarization is equal to the charge density, surface charge density produced in the dielectric. So this will become the polarization. The main formula of polarization is this: the dipole moment net is generated in this whole dielectric, the sum of all the dipole moments divided by the volume, that is the dipole moment per unit volume, that is the average value. And there is electric displacement equation. There is one term used in this capacitor case which is called dielectric displacement, electric displacement. The term is electric displacement. This term denoted by d, this vector is written as epsilon naught E vector. Here we will use only epsilon naught. We cannot use epsilon naught k at this place, never. There we will always use epsilon naught. So the displacement vector, electric displacement vector, this quantity is written as this value plus this value. This is polarization, this is polarization value, and this is epsilon naught into E vector. This is the formula of electric displacement vector, and this can be written as, since this can be written as epsilon naught into k E vector, where this is right now when I produce the electric field in this direction, the negative charge will be in this direction. So the dipole moment will also point in the direction of applied electric field, right? So okay, fine, these two are in the same direction. This value is like this, and we know that the value of electric field is equal to sigma minus sigma p upon epsilon naught, because the sigma p reduces the value of the charge here, surface charge density. So in this medium, the effective surface charge density will be taken as this minus sigma p and this sigma. So this total value will be acting as the net net surface charge density. So this will be the surface charge density sigma divided by the epsilon naught, and this can be written as sigma minus this value is simply I can multiply with n vectors. So to satisfy these values, this can be written as the polarization vector, and this can be written as n cap into polarization vector divided by epsilon naught. So this and this we get electric field into epsilon naught plus p dipole p vector is equal to sigma into n cap. This equation is equal to this electric displacement vector. That this value sigma, which this is equal to this d value. So the charge produced on this plate, the surface charge density of this plate can be written as the electric displacement magnitude as sigma. Mm. So we can write the magnitude of d as sigma also according to this, and this follows this equation. We used this equation to we used this equation and then this fact to derive this relation, and this is called this electric displacement vector. And there is one quantity xi e, which is called electric susceptibility. This is given as epsilon naught k minus 1. This value is called electric susceptibility, and the importance of this, the need of this electric susceptibility is that the p vector, the polarization, can be written as xi e into this electric field vector. So to write this polarization, we can, using this electric field equation, this is the net electric field equation. The net electric field present in the medium, and this is the polarization. This can be equated using this electric susceptibility value, and electric susceptibility is epsilon naught. This is the dielectric constant value of the medium minus 1. That's it. So the main thing here is that this is this value, this relation, and this thing we have told earlier also, nothing else. This is t, where this equation from this I have derived, and this looks totally identical to this equation. So we can say that the sigma and d both are same thing. So that's why this. Then the chapter is over. But one more thing about this chapter we can do is charging of, no, we will do in the next chapter, electricity.